Section 1.7, combinations of functions and composite functions. So our objective for this section is to find the domain of a function, combine function using the algebra of functions, specifying the domains, which means addition, subtraction, multiplication, and division of functions. Then in objective 3, we're going to form composite functions, which means functions inside of other functions. 4, we're going to determine the domains for these composite functions. And finally, we're going to write functions as compositions and use function decomposition. So first, the domain of a function. Functions that model data often have their domains explicitly given within the function's equation. Okay, so what that means is that if we are modeling a real-world situation, like in a word problem, like something that looks at something very specific, we usually see the domain spelled out for us. So it's going to be inside the problem. The problem is going to be talking about something specific over this time period that does this certain things. However, for most functions, only the equation is given, like right there. And the domain is not specified. In this case, the domain of a function f is the largest set of real numbers for which the value of f of x is a real number. So let's look at this function down here at the bottom. And we can say that the domain of this function is everywhere that the function is defined. And for most functions, that's going to be all real numbers, except for usually division by 0 or having negative numbers underneath the radical. This gives me an undefined answer, and negatives underneath the radical give me imaginary numbers. So we're going to specifically look for these two situations. We're going to look for functions that have division by 0, and we're going to have to look for functions that have radicals, and we're going to make sure that there's no negatives underneath the radical. There is one number that I can plug into x that would make the denominator equal to 0. Okay? And that is, of course, 3. And we can show that by saying that I do not want x minus 3 to be equal to 0, so x cannot be equal to 3. I don't want it to be equal to 0. Okay? And that's what this says right here. So the domain of f, in this case, this function right here, is x such that x is a real number and x is not equal to 3. That is set builder notation. And if I want to use interval notation, I can say that the domain of f is equal to negative infinity comma 3 union 3 to infinity. All real numbers less than 3 or all real numbers greater than 3 but not equal to 3, which eliminates 3. All right. Next, let's consider a function involving a square root. Here, I want to make sure the numbers that go underneath the radical are positive numbers. So instead of saying that x minus 3, instead of setting it equal to 0, I can set it greater than or equal to 0 to ensure that it's a positive number. Now in this case, having 0 is okay because the square root of 0 is 0 as long as underneath the radical is positive. Add 3 to both sides, and I get that x must be greater than or equal to 3. And if I say that with set builder and interval notation, it looks like that. Okay, and here's my explanation from the text, is that because only non-negative integers have square roots that are real numbers, the expression under the square root sign x minus 3 must be non-negative. We can use inspection, right? We can just figure it out just by looking at it. And the domain of G consists of all real numbers that are greater than or equal to 3. Again, in set builder notation and interval notation. Okay. So finding a function's domain. If a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Exclude from a function domain real numbers that cause division by 0 and real numbers that result in an even root, such as a square root of negative numbers, even roots of negative numbers. Odd roots of negative numbers is okay. Even roots is not. So when we look for a function's domain, if we're just looking at a function, we're just going to say the domain of this function is all real numbers, unless we have division by 0 or square roots or other even roots of negative numbers. So let's find the domain of each function. Okay. So in part A, the domain of this function is all real numbers except for anywhere that makes this function all undefined. Well, there's no variables in the denominator. There's no square roots of any variables. So the domain of this function is going to be domain of f is from negative infinity to positive infinity, all real numbers. Okay. Next, this function. The domain of g is all real numbers except for anywhere that this makes this function undefined. Well, anywhere that the denominator is equal to 0 will make this function undefined. So I want to know this. I want to know where x squared minus 2x minus 3 is equal to 0. And the easiest way to figure that out is to factor it. If it's a quadratic, we can factor it using basic factoring techniques. The factors of 3 that subtract to 2. This would factor into x minus 3, x plus 1, which means that x here would be equal to 3 and negative 1. So those are the two places where x would the denominator would be equal to 0 if x is equal to either one of those two numbers. So when I make my domain, I'm going to have to skip over those two numbers. But I want every other number. The domain of this function is all real numbers except for 3 and negative 1. And I'm going to write this with interval notation. So I'm going to say the domain of g is, always start from the left, negative infinity to negative 1. I then want to skip over negative 1, so I use a parenthesis. Union from negative 1 to 3. I want to skip over 3. Union 3 to positive infinity. And there's the domain of this function. All real numbers except for negative 1, which I skip over, and 3, which I skip over. Okay. Next. Now we have a radical. Okay. So, and it's a square root. So my domain here is going to be all real numbers except for the places that make the radical negative. So I want to know, where is this stay positive or 0, greater than or equal to? And of course, if I subtract 12 from both sides, I have 3x is greater than or equal to negative 12. So x is greater than or equal to negative 4. So the domain of h is going to be all real numbers greater than or equal to negative 4. And using interval notation, I use a bracket because it says or equal to, and then to infinity. And last one. Now the radical is in the denominator. So now I want to know everywhere that makes the square root greater than or equal to 0. But I don't want it to be equal to 0 because it's in the denominator. So I just want to know this, where 14 minus 2x is greater than 0. Not greater than or equal to, because if it's equal to 0, that makes the function undefined anyway. Subtract 14 from both sides. And divide out the negative 2, remembering, of course, that when I divide an inequality by a negative number, you have to change the sense of the inequality. We have to change the direction of the inequality symbol. So now my domain of j is all real numbers where x is less than 7. So I'm going to start at negative infinity and go to 7 with a parenthesis, not a bracket. Okay? So those are our basic situations about how to tell a function's domain, right? When we have something with no special characteristics, when we have something with a 0 in the denominator, with a regular radical, and with a radical in the denominator. Okay, so let's move on now to the algebra of functions. And we can combine functions using addition, subtraction, multiplication, and division by performing operations with the algebraic expressions that appear on the right side of the equations. For example, if I start with these functions, 2x and x minus 1, these can be combined to form the sum, the difference, the product, and the quotient of f and g. And with these two very specific examples, we can look and examine the four different ways that we can combine these two functions. We can add them, taking f plus g of x, which is the same thing as f of x plus g of x. So basically, I just take these two functions, 2x and x minus 1, and I'm just going to add them together, combine like terms to give me 3x minus 1. For the difference of f minus g, I'm going to take f of x minus g of x, being careful to distribute the negative sign. I want to subtract everything in g. So when I do this, I'm going to get my answer of x plus 1. The product of two functions is just the f of x times g of x. Just distribute the 2x to get my answer of 2x squared minus 2x. Now for the quotient function, even if 2x and x minus 1, even if their domains were all real numbers, which they are, as soon as I start to divide, I have to make sure that g of x is not equal to 0. So x minus 1 cannot be equal to 0, so x cannot be equal to negative 1. So when I make a quotient function, it's always going to use, it's pretty much, unless the bottom can never equal to 0, it's going to have somewhere that the function is not defined. Okay. Now, speaking of domains, the domain for each of these functions consists of all the real numbers that are common to the domains of f and g. So using the domain of f to represent the domain of f, right, the symbol right here, d sub f, and d sub g to represent the domain of g, the domain for each function is d sub f intersection d sub g. In the case of the quotient function, we got to remember not to divide by 0, so I said that. So if we take the domain of f, the blue line, right there, and we take the domain of g, the maroon line, we want to see where they intersect, and they intersect in this region right here. So the domain of f plus g would be where the domain of f and the domain of g intersect. Okay? So to sum up this idea, the algebra of functions, sum, difference, products, and quotients. So let f and g be two functions. The sum, f plus g, the difference, f minus g, the product, f times g, and the quotient, f over g, are functions whose domain are the set of all real numbers common to the domain of f, and g, d sub f intersect d sub g, and is defined as follows. The most important thing here is notation. Okay? So don't get confused with the sum notation when it looks like this, where f plus g of x is the same thing as f plus x and g, f of x plus g of x. You're just adding the functions together. Okay? That's important right there. Okay? Sometimes you'll see a little dot in the middle like that. All right? That means multiplication. That's different than what we'll do next, which looks like this, where that is a open circle. Kind of hard to see. Let me make that a little bit better. It's supposed to be a nice open circle like that. And that is a combination function. That's putting one function inside of another function. So let's start with combining two functions with addition, subtraction, multiplication, and division. So we're going to start with my two functions, 2x minus 1, f of x, and g of x, x squared plus x minus 2. So f plus g of x is simply going to be f of x plus g of x. Now to combine these, I just take f of x, which is 2x minus 1, okay, plus g of x, x squared plus x minus 2. And then to combine them, I just add the like terms together. So we get x squared plus 3x minus 3. So f plus g of x is x squared plus 2x minus 3. The domain is going to be all real numbers because there's no variables in the denominator. There are no denominators. And there's no radicals. So no way to get a function to be undefined. Let's try subtraction. So this is f minus g of x. So that's f of x minus g of x. Okay, so that's 2x minus 1. And g of x was x squared plus x minus 2. Now, we're going to subtract these two functions, but if I do it like that, I'm going to get it wrong. Okay, so what you need to do is make sure that you're taking the first function minus the second function. And we could even have done that up here, right? We could have taken the first function plus the second function. So if it makes sense to you to separate them with parentheses, that's great. The important one is right here with subtraction because we have to distribute the negative. So that's minus x squared minus x plus 2. Okay? And when I put these all together, I get a negative x squared plus x plus 1. And again, the domain here is from negative infinity to positive infinity. There's no division and there's no radicals. Let's try multiplication. F times g of x. So this is going to be f of x times g of x. F of x times g of x is going to be, now I definitely need parentheses here, 2x minus 1 times x squared plus x minus 2. And don't forget to distribute these two. We're going to distribute the 2x 3 times, and we're going to distribute the negative 1 3 times. So it kind of looks like 2x times x squared plus x minus 2, and then minus 1 times x squared plus x minus 2. And when I distribute these out, I get 2x to the third plus 2x squared minus 4 minus x squared minus x plus 2. And now all I have to do is go through, combine all the like terms, and be sure not to miss any. Plus x squared minus 5x plus 2. Ooh, that would help, right? 2x times the 2, 4x minus x, 5x. Okay. And finally, domain is from negative infinity to positive infinity. There is no division by a variable, so nowhere to make a denominator 0, no radicals. I think we get the idea of that. Let's finish with division. So this is going to be f of x over g of x, okay, which is going to be 2x minus 1 over x squared plus x minus 2. Now, it is helpful to factor this to number 1 to see if anything cancels so I can simplify, and number 2 to see the places where the denominator is equal to 0 so I can tell where this function is going to be undefined, if it's anywhere. So when I factor this, I get x plus 2, x minus 1, which means that the denominator, x cannot be equal to negative 2 or positive 1. Because both of those would make the denominator equal to 0. So that means the domain, this is done. This is my function. Nothing cancels. Okay. All I need now is to list the domain, and the domain is going to be from negative infinity to negative 2 union negative 2 to infinity. Okay. So let's try to add a couple functions together that have a weird domain. Okay. So first, when I add these two things together, f of x plus g of x, that's going to be x plus 3 plus radical x minus 2. Those are not like radicals. I can't do anything with them. So that's as simple as it gets. To find the domain for part B, we need to first look at the domain of f and g, and we need to see where they intersect. The domain here is everywhere that makes this positive. Well, before we get to domain, we can say that I want x plus 3 to be greater than or equal to 0. 0 is okay. So x has to be greater than or equal to negative 3, which makes the domain of f from negative 3 to infinity. And up here for g, I want x minus 2 to be greater than or equal to 0. So x has to be greater than or equal to 2. So the domain of g is from 2 to infinity. And the domain of f plus g is going to be where these two domains intersect. Okay, so what they have in common. Well, negative 3 is in this domain, it's not in this one. Negative 2 is in this interval, negative 1, negative 0, or yeah, negative 1, 0, 1. 2 is the first number that's in both of the domains, and now we have the place where they overlap, and now we have our intersection. So the domain of this is only from 2 to infinity. Okay, and if I look at this function right here, my function of the two of f plus g, I can sort of tell that if I plug in a 1 into this function, that's going to make this negative. But if I plug in a 2, that makes this 0, and that still makes this a number that is not negative, which is what I'm looking for. Okay, so this g, this function, is the more restrictive. It has less numbers in the domain. So that's what I'm going to look for when I have the intersection. Okay. Okay. Let's look at a quick word problem and applying the algebra functions to a real-world situation. So in the textbook, in the opening section of the textbook, there was a model about the number of births and the number of deaths in the United States from 2000 to 2009. Well, if I look at this, the domain of this function is really simple to find out because I read the problem and it says the domain is from 2000 to 2009. So X years after 2000. So the answer here is going to be, or the domain here is going to be 0 through 9. Okay? So pretty simple to get a handle on that. Okay? So write a function that models the change of U.S. population. So if I want to know the change of population, well, that would be a subtraction. Right? If I take the number of people that are born minus the number of people that die, I now have a function that models both. And I can set this up as the first function, 2.6x squared plus 49x plus 3994 minus the second function, negative 0.6x squared plus 7x plus 2412. Run out of room there. Okay. And if we add these together and subtract, I would get negative 2x squared plus 42x plus 1582. Okay. So this models the change in population for X years after 2000. So if I wanted to, say, use the function to find the change in US population in 2008, I could very easily figure that out by finding births minus deaths of 8. 2008. Okay? So I start with negative 2, 8 squared plus 42 times 8 plus 1582. Okay? And if I work all this out on my handy calculator, I get 1790. Okay? Not a real crazy problem here, but the idea was to take a function combination, two functions subtracting each other, and you could do these separately, right? You could plug 8 into there, 8 into there, and subtract the two answers, which would be perfectly fine. Because remember that b minus d of 8 is also b of 8 minus d of 8. So that would work as well. This just seems to be a little bit faster. Okay, so let's move on to composite functions. Okay, there's another way of combining two functions. And to help you understand this new combination, suppose that your local computer store is having a sale. The models that are on sale either cost $300 less, so here's my first function, or 85% of the regular price, 15% off. There's my second function. And I can clearly see that f and g are calculated for me. I'm going to start with the price. I'm going to subtract 300 bucks. Okay. I'm going to start with the price, and I'm going to take 85% of the regular price. Okay, so I'm going to take off 15% to get my new price. So in one case, I'm going to subtract. In the other case, I am going to multiply. Okay. So at the store, you bargain with the salesperson, and eventually she makes you an offer you can't refuse. The sales price will be 85% of the regular price, followed by a $300 deduction. So now you can see that these two functions are going to act together. 85% of the regular price, followed by a $300 reduction. So in terms of the functions f and g, this offer can be obtained by taking the output g of x is equal to 0.85x, or this, and using it as the input into f. So instead of x right there, I'm going to replace x with 0.85x. Instead of the input of x, my input is going to be 0.85x. And that kind of looks like this, with g of x, which is this function, inside of f of x. That is the key to a combination function. Okay, let's use our notation, and we're going to read this equation as f of g of x. So this equation right here, this last one, whoops, right there, we're going to read it as f of g of x is equal to that function. So f of g of x is equal to 0.85x minus 300. We call this f of g of x the composition of the function f with g, or a composite function. So kind of a mouthful, the composition of the function f with g. So more often, we write it like that, okay? And we read this as f of g of f of g of x, okay? Now, be very aware that that is an open circle, not a dot. A dot means multiplication. This open circle like that, kind of looks like a degree symbol, but a little bit lower. It's always in the middle, means a composite function. F composed with g of x. This goes inside, and we're going to put that into f. So let's look at this with numbers. So remember my functions here was g of x was 0.85x, and f of x was x minus 300. So what we're doing is we're taking 1400, putting it into g to give me 1190, and then 1190 goes into f to give me 890. The input goes into the first function. Your answer, the output, is what goes into the second function as the second function's input. Okay? And so this verifies that the computer that regular sells for 1400 is on sale for 890, subject to both discounts. Okay, so let's look at this in a formal definition. Okay, so the composition of the function f with g is denoted by f of g, and it is defined by the equation f of g of x. And another way to write that is like this. These mean the same thing. Okay, so if you like the way this looks, that's fine. Sometimes you'll see it like the first way. Sometimes you see it like the second way. It means the same thing. The domain can get a little trickier. Okay, so the domain is the domain of the domain of the composite function f of g is the set of all x such that x is in the domain of g, because that's my input into g, and then that's my input into f. So g of x must be in the domain of f, and we'll see what that looks like in a second. Let's first get a little visualization of what this looks like, and we can see that if I want to compose f with g, I can input x into g. So I'm going to go into the function. I'm going to do all the calculations, whatever happens, and this function is going to spit something out. This output then becomes the input into function f. This function is going to do whatever it does, and now my output pops out as f of g of x. Now g of x must of course be in the domain of f in order to put it into this function of f. And again, we'll look at that in a minute. Let's first see how we do this. Okay. So let's first take f of g of x. So remember, that means f of g of x. So g of x is going into f of x. G of x is going into f of x. Okay? So basically, we're saying that instead of x, my new input becomes g of x. So it's 3 times g of x minus 4. Well, g of x is a whole function. So it becomes 3 times x squared minus 2x plus 6 minus 4. Instead of the variable x, my input becomes this whole function g of x. So we're replacing the x in f of x with the whole function from g. Okay? And now we just combine like terms. So I get 3x squared minus 6x plus 18 minus 4, which then simplifies to 3x squared minus 6x plus 14. Okay, let's go the other way. Let's do g of f of x. So now this means g of f of x. So now f replaces the variable in g. Now this one gets a little more complicated because I got a squared. Okay, I got a quadratic. So this turns into, instead of x squared, it turns into 3x minus 4 squared minus 2 times 3x minus 4 plus 6. Instead of the variable x, I write the function f of x. So these x's get replaced with that. And now I just simplify. There we go. Of course, remembering that when I square a binomial, don't forget that it has a middle term. Minus 24x plus 16 minus 6x, distribute the negative 2, plus 8 plus 6, which gives me my function of 9x squared minus 30x plus 30. Okay? Let's try with some numbers. Maybe this will help. A little bit of numbers here. Okay? So now g of f of 1. So I want to find, oops, I want to find g of f of 1. Let's first find f of 1. So that means that I'm plugging 1 into the f function. 3 times 1 minus 4, which gives me negative 1. So f of 1 is negative 1. Now I want to, because this is equal to this, a little substitution means I now want to find g of negative 1, right? Because f of 1 is the same thing as negative 1. Okay? So I can plug negative 1 now into the g function. So g of negative 1 is going to be negative 1 squared minus 2 times negative 1 plus 6, which gives me 1 plus 3 plus 6. Sorry, 1 plus 2 plus 6, which is 9. So I can do it this way. I could plug 1 into f and then the answer into g. I also went through all the trouble of getting g of f of x. So if I wanted to find, oops, if I wanted to find g, if I wanted to find, get rid of this, g of f of 1, I could have plugged it right into this function because that's g of f of x, which would give me 9 times 1 squared minus 30 times 1 plus 30, which is 9 minus 30 plus 30, which is just 9. Same thing that I got here. Okay. So either way you want to try to get these answers, you'll still get to the same place. So sometimes just plugging in the numbers into one function, then the other function is a little bit easier. Sometimes it's easier just to get the composite function and then plug the numbers in. Now all these functions, the domains were all real numbers because there was nothing, no variables in the denominator, and there were no radicals. Let's try one that doesn't have that. Okay, so we need to be careful in determining the domain for a composite function. Exclude the values from the domain of f of g of x. The following values must be excluded from the input of x. If x is not in the domain of g, right, the first function, right, we're going to go inside out, then it must not be in the domain of f of g. Any x for which g of x is not in the domain of f must not be in the domain of f of g of x. So what does that mean? It means that any x that makes g undefined is excluded, and any g of x that makes f undefined is excluded. So when I look at these two functions here, you might be tempted to say, well, okay, 0 makes g of x undefined, and 1 makes f of x undefined. So it's all real numbers except for 1 and for 0. But that's not necessarily true. So when we find f of g of x, Remember, we're plugging inside out. We're plugging g into f. This means f of g of x. So when I do that, I take g, oops, I take g and put it there. So it becomes 2 over 3 over x minus 1. I could leave it like that. I probably shouldn't because that's pretty ugly. So in order to clear this up, I'm going to multiply the top and the bottom by the least common denominator of all three terms. So the denominator right here would be a 1 if I wrote that as a fraction, a 1 and an x. So I'm going to multiply the top and the bottom by x over x to give me 2x over x times 3 over x is 3. X times negative 1 is x. And so there's my function, my composition function, f of g of x. Okay, so the domain of this is going to be anything that makes that inside function undefined, that makes g, this first one, undefined. And we can clearly see here that x cannot be equal to 0. Okay, then I want to find anything else that is going to make this g of x, this function, make that one undefined. Because remember, we're putting the g into f. So I basically want g of x not to be equal to negative 1. Not f. I want, so negative 1 is not, or sorry, 1 is not excluded from the domain because I'm going to plug 1 into my g of x. 3 over 1 is 3, which would then travel over there. So 1 does not work. But if maybe I could figure out a place where g of x would be equal to negative 1, like if I plugged a negative 3 in there, now, whoops, not negative 1, positive 1, okay? So now if I plugged a 3 in there, now I would get an undefined function. And you can kind of see that because in my combination function right there, x, negative x cannot be equal to negative 3, so x cannot be equal to 3. Okay, so these are the two numbers that I want to exclude from my domain. The place where this is undefined and where my combination is undefined. Not f of x, not my outside function, okay? So my domain here is all real numbers except for 0 and 3. So the way I say that is from negative infinity to 0, union 0 to 3, union 3 to infinity. Okay. All right. So let's take a look at a couple random functions here. H of g of x, right? So g would go into h. So the way I would set this up would be to take g and to plug it in to h. Okay. And then, of course, remembering that there's a middle term, 12x plus 9 plus 6x plus 6 to give me 9x squared plus 18x plus 15. Okay, so we can go about plugging all different sorts of things in order to get these composition functions. This one's a little bit harder because now we're plugging a function into a function into another function. So watch this. So g of t minus 3. So g of t minus 3 would be equal to 4 times t minus 3 plus 1. Right? I'm plugging t minus 3 into g, which would give me 4t minus 12 plus 1, which is 4t minus 11. Then this goes into f. So now I get 4t minus 11 squared plus 2, which is going to be 16t squared minus 88t plus 121 plus 2 to give me my final function of this. Okay. And before we do our last topic, let's try one more function. Here's f of x, and we have 4 over x plus 2. Here's g of x, which is 1 over x. Let's find f of g of x, and then let's talk about the domain. Okay, so f of g of x would be g goes into f, so 4 over 1 over x plus 2. Multiply the top and the bottom by x to clear the fractions and to give me a nice clean function. 1 plus 2x. Okay, so now the domain of this is going to be all real numbers except for 0, because x cannot be equal to 0 there, and whatever makes my combination function equal to 0, the denominator here. So that's 2x is equal to negative 1, not equal, right? And divide out the 2, that's x cannot be negative 1/2, which again, if I plug negative 1/2 into here, that's not what I'm looking for, right? I want to plug it into here to give me a negative 2, and then the negative 2 plugs into f of x to make the f of x function undefined. So you can't send an undefined number from g to f, and then you can't have the answer from g plug into f and give you something that's undefined. So my domain is from negative infinity to negative 1/2 union negative 1/2 to 0 union 0 to infinity. Okay, so let's finish this section with decomposing functions. Okay, so when you form a composite functions, you compose the two functions to form a new function. It's also possible to reverse this process. That is, you can decompose a function and express it as a combination of two functions. Although there are more than one right way to do this, there's often a natural selection that comes to mind first. For example, if you consider the function 3x squared minus 4x plus 1 all to the 5th power, I can clearly see a function here, something raised to the 5th power. Okay, so when you're decomposing functions, you basically want to look for x to a power and then some sort of algebraic expression. Okay, usually that's the easiest way to decompose a function. And we can do it here by making f of x x to the 5th, g of x is equal to 3x squared minus 4x plus 1. X to a power, algebraic expression, and then if I put these two together as f of g of x, g into f, then I would have my original function back over. So the function h takes this 3x squared minus 4x plus 1 and raises it to the 5th power. A natural way to write h as a combination is to raise the function to the power of 5. Okay, so let's try it. So there's a natural way here, and that's to have x to some power and then have an algebraic expression underneath inside something. So here's my algebraic expression. So f of x could equal x squared plus 1. G of x would be equal x to the 1/3 power, or, let's not get fancy, just cube root. So then if I want to make my h function, h of x would be equal to f inside of g. So g of f of x, right? If I take the f function and I put it inside of g, I would get my composition function. Okay? And we can do this with all sorts of functions. You look for the main function on the outside, you look for the function in the middle, and you can break them down into any sort of decomposition. Okay? Uh, let's try one more of those real quick. And let's look at this, 3x minus 4. So here's h of x, right? I could split that into f of x and g of x. I look for the function on the outside and the function on the inside. And then my function would be f of g of x to give me h g inside of f. Okay, and that was the end of section 1.7, combinations of functions and composite functions.